Good afternoon, everyone. Thanks for inviting me. I'm Christina, and today I will talk about some ways to improve resource efficiency in large-scale data centers through cluster management techniques. So essentially what I want to talk about is how can we take curves that look like this and shift them to the right. Now what I'm showing in these two graphs is the distribution of CPU utilization for a large cluster at Twitter on the left, and then the graph on the right shows a similar thing and was reported a few years back from Google. And the thing to note here is that the y-axis is the fraction of time for which the cluster operates at a given utilization. And for the majority of time, both clusters are at about 10 to 20, 25, maybe 30%. Okay? So they're mostly underutilized. Now, low data center utilization is the one problem that we want the cluster manager to solve. And it mostly is the result of over-provisioning resource reservations by the users that submit applications. But it's not the only problem that we have. The other problem is that data center applications often have unpredictable behavior, unpredictable performance, or performance jitter, which comes as a result of either interference from other workloads if the cluster is shared, or from being mapped to a different platform than the application was mapped the previous time. So what I want to talk about today is how the cluster manager, which is the system that orchestrates where applications get placed and how they're sized in a large cluster, can determine how different amounts and types of resources will affect the performance of each incoming application, and take those resource preferences and resource needs into account to size the allocations more tightly so that we don't have the over-provisioning problem. And do that while still maintaining the quality of service constraints that data center applications have. So first of all, let's look a little bit more into the utilization analysis that I showed in the beginning. This utilization data comes from a large production cluster at Twitter, and was collected over the past summer here. And this cluster is managed by Mesos, and it runs mostly user-facing latency-critical applications. So these are not batch Hadoop-like workloads. Okay? And what I'm showing in this graph is the distribution of the utilization for different fractions of the servers for each week in a 1-month period. So the way to read this graph is that about 80% of the machines operate at less than 20% utilization. And why do we care about this? Well, first of all, we care about it because we paid about 60 to 65% of the total cost of ownership into buying those machines. So we don't want to be operating them at 20%. But more than a cost argument, it's a scalability argument, because the moment we need twice as much compute capability out of our system, we need to either build twice as many data centers or add twice as many servers in our existing data center. And that is not a scalable approach because there are not that many electricity facilities that can provide us easily with 20, 30, or 50 megawatts of power. So when somebody looks at this graph, he might think that it's the cluster manager that is doing a poor job at allocating or placing applications into the machines. So we wanted to see if that's actually the case. And we went and looked at what is the amount of resources, CPU and memory resources, that are actively being used during this 1-month period in the cluster, and compared that with the amount of resources that users reserved when they submitted their applications. And this is what we get. So the graph on the left shows the amount of CPU resources used in green and reserved in red, and then the graph on the right is the same for memory. And this is cluster-wide and for the entire 1-month period. And the thing to note here is that especially for CPU, there is a 3 to 5x over-provisioning between the amount of resources that users ask for and the amount of resources that the applications end up using. And the problem with this is that the cluster manager thinks that the system is running close to capacity when it's actually pretty lightly loaded. And the reason why this happens is because the majority of applications that were submitted to the cluster during this 1-month period over-provisioned significantly their reservations. So about 70% of the jobs asked for more resources than what they ended up using, and often they asked for 10 to 12x more resources. So only very few applications reserved the correct amount of resources that they ended up using. Now, this is the data from Twitter, but actually other companies have reported similar results. So these graphs show focus on the pink lines here. So they show the amount of CPU resources used and allocated for Google, and then the same for memory. And you can see that, again, there is a 2 to 3x over-provisioning. Okay, so far I've blamed this on the users not knowing what resources to ask for, but can we just blame it on them and stop here? Well, not really. It turns out it's actually pretty difficult for a user to figure out what is the appropriate amount and type of resources that he needs for an application to satisfy a quality of service constraint, even if it is his own application. So let's assume that a software developer has an infinite amount of time and he wants to figure out how his application, what resources he should ask for his application. What would he have to do? So let's say that he has this one application, and first of all, he wants to see how the performance of the workload will change as we add more cores, as we give it more cores in a single node. So he would have to do this experiment. Now, and we see that after a point the performance levels off. Now, if the cluster does not have a single platform, it has another platform, then he needs to repeat the same experiment for the second platform as well. If this is an application that can be distributed across multiple nodes, he also needs to know how the performance will scale as the load is distributed across multiple servers. If the load can change, he needs to know how the performance will change with different characteristics, intensities, or sizes of the input data set. And then finally, if this is not an isolated cluster, if it's a shared cluster, he also has to know how the performance will change with different intensities or types of interference. And note that this is a multiplicative experiment, and it needs to happen every time there's a new software release, every time something significant changes in the operating system, and every time a new platform is rolled into the data center. So this is a pretty complex analysis for any application developer to do. So what is the easiest way to sidestep all these complications? Is just to over-provision the reservations to the point where they don't matter. However, what if we go back in the way we think about cluster management and account for the application characteristics and the application preferences when we allocate resources and when we assign resources to workloads? So essentially what we want is to determine what are the performance resource trade-offs for each incoming application. And then once we have this information, we can do other things as well. For example, we can do load prediction, which can anticipate the arrival of high loads and either reclaim unused resources or resize an allocation to accommodate the increase of the incoming load. And then we can go even further than that. So the current approach is that the user is expected to specify how many resources he wants for his application. But what if we can make the life of the user a bit easier? So what if we can have him, instead of specifying the raw resources that he needs, to have him specify a performance target that he wants the application to meet? So what do I mean by a performance target? Obviously, different applications care about different things. So a performance target for a batch Hadoop-like workload can be something like the completion time or the progress rate, or for a latency-critical application like Memcached, it can be the queries per second under a latency constraint for the 99th percentile latency. And now what we want is the cluster manager to take those performance targets and translate them into resources. Now, have we made the system more resource efficient? Well, not really. Again, we just passed the hot potato on the cluster manager side. So the life of the user is easier now, but the cluster manager still needs to figure out how to translate those performance requirements into resources. So let's see what information we can use to do this translation. First of all, we can use a little bit of profiling signal. Every time a new application is submitted in the system, we can profile it for a little while. Or if there is repetition in workloads, the profiling doesn't need to happen online, it can happen offline. Now, this will give us a little bit of information about the new application, but it cannot give us the full exhaustive information that we would get if we were to do the analysis that I showed in the beginning. So how can we go from this profiling signal to the full information? Well, it turns out the system already has a lot of knowledge about applications it has previously seen, which we can use to find similarities between the new workload and previous applications that have been scheduled in the system, and give better insight to the cluster manager on what are the performance resource trade-offs for this new incoming application. So this already starts sounding like a classification problem, this similarity finding. It's pretty similar to what happens in a system like Netflix or any movie recommendation system or Amazon, where you go and rate a couple of movies, and then the system compares you to the previous users and finds similarities between you and previous users and starts recommending more movies or more items that you're likely to enjoy. So let's explain how let's see how a system like this would work for a movie recommendation system. So the recommendation system will start with some very sparse information, which is that each user will only rate a couple of movies. He cannot rate the entire database. And then we'll use an approach that is commonly used in recommendation systems, which is called collaborative filtering. So specifically, we'll use singular value decomposition and PQ reconstruction to derive what are the missing entries. So what would be the ratings that this user would give if he were to rate every single movie in the database of the website? And then finally use SVD to figure out from those ratings which are the ones that he's likely to give high scores to with high confidence. Now let's see if we can apply a similar approach into cluster management. So what do we need to know here? We don't want to recommend movies to users. What we want is to figure out four things. We want to figure out what is an appropriate hardware platform for this new application, what are acceptable levels and types of interference given its characteristics, what is a suitable amount of resources within a node, so what is an appropriate scale-up configuration or allocation, And then how many nodes should we distribute the load across? So what is an appropriate scale out configuration? And note here that I've decomposed the cluster management problem into 4 components. The reason why we rather do these 4 parallel classifications as opposed to a single exhaustive one is that obviously the complexity and the overhead of the single exhaustive one would be significantly higher, and actually turns out that the accuracy, the improvement in accuracy that it would offer does not justify the increased overhead. So okay, we're using this classification, but we need to know how accurate the output of the classification is compared to actually doing the exhaustive characterization. So let's see. I'm showing here a small snapshot of the validation that we did. So basically what we compare here is for different types of applications, and batch distributed is something like Hadoop, latency critical is something like Memcached or Cassandra or a web server. And what I'm comparing is for each classification type, what is the difference between the performance that the classification engine estimated and the actually measured performance when that application runs with a given allocation or assignment. And the thing to note here is that on average, the errors, the estimation errors are actually pretty low. There are a couple of cases where the maximum error becomes a little bit higher, and the reason why this happens, it's in the scale-out case, the reason why this happens is because we want to keep profiling overheads low. So profiling will require some resources to gain that initial sparse signal about a new application. And if a submitted job is very large, then because we don't want to profile across a huge number of nodes, the estimated performance will deviate a bit from the actual performance. And the way we address this is by introducing a simple feedback loop that updates the classification information once this large job runs in the cluster. So let's see what are the different steps of cluster management. First of all, we have a user, and he arrives with his application, and he specifies a performance target that he wants that application to meet. Okay? Now the cluster manager will take that application, and it will generate a little bit of profiling signal on it to generate this sparse input signal that is given to the classification engine. Now the classification engine takes this sparse input signal and transforms it into a dense output signal, which essentially will tell us what are the performance resource trade-offs for each of the 4 classification types that I showed before. And then finally, a simple greedy algorithm, and let's assume it has full visibility in the server state, will take those recommendations and search for the best available resources given the resource preferences of that application. So what I'm showing in this graph is the overhead that comes from each step of the cluster management process. And you can see that most of the overhead comes from profiling, so from obtaining this small sparse signal that we want for each new application. Now, if the applications submitted in the cluster are repeated, profiling does not need to happen online, it can happen offline. The real overhead that we're interested in is how much does the classification add. So how much overhead do we get from generating the full information about the resource preferences of each workload. And you can see that on average this overhead is pretty low, and the numbers that I'm showing here are for a few thousand applications and a few thousand machines. So in terms of implementation, this system is implementing a few thousand lines of code. It supports various frameworks like Hadoop, Spark, and Storm. And it doesn't require any changes in existing frameworks. It just has some framework-specific code to interface with their APIs. And then, although the results that I'll show here are for a standalone framework, the techniques themselves, for example, the recommendation system, are pluggable to systems like Mesos. So we've evaluated the system with a few different scenarios. I'm actually going to focus on a more general case here. So imagine you're a public cloud provider and you have 200 EC2 servers, and they have 14 different server types, server configurations. And 1,200 applications arrive in your system with 1 second inter-arrival times. And these are applications of different types. And what we want to see is, and they have performance targets that they have to meet. So they have QoS targets. And what we want to evaluate is how high is the cluster utilization and how closely does the cluster manager satisfy the performance targets of each individual application. Now, before I show you the results, I want to note one thing here, which is that some of these applications have some different characteristics, which makes them a little bit more difficult to schedule. And those are 2 things. First, they're latency critical, which means they're much more sensitive to incorrect allocations or assignments. Their performance will suffer quicker or faster or more than batch applications like Hadoop. And the second thing is that these are stateful applications, which means if the allocation is incorrect and you need to reallocate in a different machine resources, then you potentially have to migrate a significant amount of state. So what can we do about this? Well, actually, it turns out that applications that are fed with user traffic tend to have pretty predictable behavior that can be modeled over time. So that is what we looked at here. We looked at a few different algorithms to see if we can predict what is the near future resource usage for these different applications. And for now, I'm focusing on CPU and memory, but a similar approach can be applied in network or disk usage as well. So I'm just going to focus on 2 techniques here, and I can talk about the rest of them offline. So first of all, we looked at the wavelet transform-based prediction, which is it's a supervised learning approach. And basically, you can think of it as a more general Fourier transform. What it does is it takes an initial resource signal. So as an application starts running in the system, we trace its resource usage. It will decompose that signal into individual wavelets and the approximation signal. And then for each one of those, we have a simple Markov chain that takes that signal and predicts a little bit into the future. And then finally, all those predicted signals are aggregated for the final predicted signal. And this approach tends to work very well for applications that have repeated or periodic behavior, but some of these workloads, some of the data center workloads actually have abrupt changes in their load. So for those cases, we looked at a non-supervised, an unsupervised learning approach, which is classification-based. So essentially, we identify a few characteristic load patterns in the time series of the resource usage of an application. And then at runtime, we try to identify those patterns in the resource usage of the workload. So let's see a very simple example. For example, here, first it would identify class 3, then class 1, then class 2, etc. And it turns out that in the end, what we use for the load prediction is a combination of those 2 techniques to cover both the repeatable periodic signals and the signals with more abrupt changes. So just to show you a very simple example of how this would work, this is an instance of memcached, and it's running over a 24-hour period, and I'm showing here the load of the application. So the black line shows the actual load that the application is putting on the machine. And then the red line shows the predicted signal, so the predicted load by the load prediction scheme. And here there is no predicted signal because it has to start training a little bit, but what you see after that is that the predicted signal actually follows the target load or the actual load pretty closely, and you can see it's a little bit shifted to the left exactly because we need to predict before the arrival of the increased load. So what can we do with the load prediction? So in the system that I'm describing here, we're using load prediction to preemptively, to be proactive about state migration. So start migrating state before the arrival of the high load. In a system like Mesos, which is reservation-based, what we can do is use the load prediction to see how many resources will be unused in the near future and reclaim them and give them to some low priority or other applications. And obviously, we have to account for some resource lag for either mispredictions or unexpected spikes in utilization. Okay, so let's go back into the scenario that I showed before. So I'm going to play a little demo to see how this system works. So let me first explain what the different graphs are. Okay, so this is the core allocation map for Quasar, which is the performance-centric system. So each large square is an instance. Each small square inside the instance is a core. And instances are orders from small to extra large. Different colors correspond to different applications. And I'm also showing the same for a reservation-based system, which is not Mesos. It is a baseline reservation-based system where the user has to request resources. And then the cluster manager allocates those resources in the machine with the most available resources. Now, I'm also showing the average cluster utilization at each point in time from 0 to 100%. And then in terms of performance, I will show performance histograms. And the way to read this is that each horizontal bar here corresponds to the number of applications that have completed at that point in time and achieved a certain level of performance. So the top bar means that those applications got within 5% of their QoS. So that is what we want to see. We want to see most applications added in the top bar. And then finally, the progress bar shows how far into the experiment we are. Okay, so the ideal behavior that we want to see is high allocation, high utilization, and most of the applications in the top bar. So let's see how this works. Okay. So at this point in time, both systems are in the warm-up phase. So applications are arriving in the system and get scheduled. And the slightly weird thing to note here is that while allocation seems to be pretty similar in both systems, utilization is actually quite different. And the reason why this happens is because in the reservation-based system, allocations are significantly over-provisioned, so fewer workloads can be accommodated. Now, at this point, the first applications are starting to complete, and the thing to note is that while with a performance-based system, most applications get very close performance to what they asked for. With a reservation-based system, the histogram is more spread out. So some applications will still get good performance, either because they're insensitive to resources or because they were lacking, but most workloads will get some performance degradation. Okay. And now if we wait a little bit, you'll see that the system on the left has started entering the teardown phase, which means that most workloads are starting to complete, while the system on the right still is mostly fully allocated. There are two reasons why this happens. The first reason is because reservations on the right are over-provisioned, fewer workloads are accommodated, so some applications have to be held at admission control. The second reason is that because the applications on the right run lower than their QoS, they also take longer to complete. Okay, so this just summarizes the results from the demo. So I'm out of time, I think, so I'll just leave the conclusion slide up.